NEC Section 250.32 Paragraph 2 permits supply conductors to be run without an equipment ground for multiple buildings on a single service, provided that certain conditions are met. These conditions include the building having a zero-sequence ground fault detection system and the service being provided from a grounded transformer. This means if your existing building is a zero-sequence ground fault system and is being fed from a 480/277 volts utility service, which typically includes a grounded transformer, then NEC Section 250.32 Paragraph 2 permits the new meter board to be added without replacing the service conductors and adding an equipment ground. It is important to consider the additional factors involved, such as local code requirement. Check with your local code enforcement authority to ensure that they do not have any additional requirements for equipment grounding. Consider also safety best practices. It is generally good practice to install an equipment ground for all electrical equipment, even when not required by code. This provides an additional level of safety in the event of a fault. Consider future expansion or upgrades. If the building is planned to be expanded or upgraded in the future, it may be advisable to install an equipment ground now to avoid potential difficulties later. In summary, based on the NEC and the information provided, it is permitted to install the new metered board without replacing the service conductors or adding an equipment ground if a zero-sequence ground fault detection system and is being fed from a 480/277 volts utility service is present. However, consider the additional factors discussed to determine if it is the best course of action for the situation. The NEC, or National Electrical Code, is a comprehensive set of standards and guidelines for electrical wiring and equipment installation in the United States. It is published by the National Fire Protection Association (NFPA) and updated every 3 years. The NEC aims to ensure electrical safety and prevent fire hazards. Article 250 of the NEC deals specifically with grounding and bonding. Grounding is the intentional connection of electrical circuits and equipment to the earth, while bonding is the connection of non-current carrying metal parts to create a low impedance path for fault current. Grounding and bonding are crucial for protecting people and equipment from electrical shock and fire. The purpose of grounding is to provide a low impedance path for fault current to flow back to the source, which allows overcurrent protective devices like circuit breakers or fuses to quickly trip and to energize the circuit. This prevents dangerous voltage buildup on metal parts that could cause electric shock if touched. Bonding ensures that all metal parts of an electrical system are at the same electrical potential. This eliminates voltage differences between metal parts, which could also cause electric shock. There are several different types of grounding systems, including grounded and ungrounded systems. Grounded systems have one conductor, typically the neutral, intentionally connected to the earth. Ungrounded systems do not have any conductors intentionally connected to the earth. Grounded systems are more common because they provide better protection against electrical shock. However, ungrounded systems can be used in certain applications where ground faults are not desirable, such as in critical healthcare facilities. In a grounded system, the neutral conductor is connected to the earth at the service entrance. This connection is called the grounding electrode. The grounding electrode can be a metal rod, pipe, or plate buried in the earth, or it can be the metal frame of the building if it's effectively grounded. The size of the grounding electrode conductor is determined by the size of the service entrance conductors. The NEC provides tables that specify the minimum size of the grounding electrode conductor based on the size of the service entrance conductors. In addition to the grounding electrode, all metal parts of the electrical system must be bonded together. This includes metal conduits, metal enclosures, metal equipment frames, and metal water pipes. Bonding is typically accomplished by using bonding jumpers, which are short lengths of wire that connect the metal parts together. The size of the bonding jumpers is also determined by the NEC. The NEC also requires that all electrical equipment be listed and labeled by a recognized testing laboratory, such as Underwriters Laboratories UL. Listing and labeling ensure that the equipment has been tested and found to be safe for its intended use. It's important to follow the NEC when installing and maintaining electrical systems. Failure to follow the NEC can result in electrical shock, fire, and other hazards. If you're not familiar with the NEC, it's best to hire a qualified electrician to perform electrical work. The section of the NEC you cited, 250.32, provides specific requirements for grounding and bonding in detached buildings or structures. Let's break down the key aspects of this section. First and foremost, 250.32 addresses situations where you have a separate building or structure that is supplied with power from another building. This is common in residential settings with detached garages or workshops, and in commercial or industrial complexes with multiple buildings. The general rule is that each building or structure must have its own grounding electrode system. This means that you need to install a grounding electrode, such as a ground rod or ground ring, at each building and connect it to the building's electrical system. The grounding electrode provides a path for fault current to return to the source, which helps to protect people and equipment from electrical shock. However, there are exceptions to this general rule. One exception, as you pointed out, is where the buildings or structures are supplied by a single service and certain conditions are met. In this case, you may be able to run the supply conductors without an equipment grounding conductor. This exception is based on the idea that if the buildings are close together and supplied by the same service, the impedance of the grounding path will be low enough to provide adequate protection without a dedicated equipment grounding conductor. The conditions that must be met for this exception to apply are: firstly, the buildings or structures must be under the same ownership or management. Secondly, a grounding electrode system must be installed at each building or structure. Thirdly, the grounded conductor, usually the neutral, must be connected to the grounding electrode system at each building or structure. And finally, a zero-sequence ground fault detection system must be installed to protect the supply conductors. If all of these conditions are met, you can run the supply conductors without an equipment grounding conductor. However, it's important to note that this exception is not always the best option. In some cases, it may be safer and more reliable to install an equipment grounding conductor, even if it's not required by the NEC. An equipment grounding conductor provides a dedicated path for fault current to return to the source, which can help to reduce the risk of electrical shock and fire. In addition to the requirements in 250.32, there are other NEC sections that may apply to grounding and bonding in detached buildings or structures. For example, 250.50 requires that all grounding electrodes be bonded together to form a grounding electrode system. This helps to ensure that all metal parts of the electrical system are at the same electrical potential, which reduces the risk of electrical shock. The NEC also provides requirements for the size of grounding and bonding conductors. The size of these conductors depends on the size of the supply conductors and the type of grounding electrode system. It's important to follow the NEC requirements for conductor sizing to ensure that the grounding and bonding system is effective. Ground fault detection systems are designed to detect ground faults, which are unintentional connections between a current carrying conductor and ground. Ground faults can be caused by damaged insulation, loose connections, or other factors. When a ground fault occurs, current flows through the ground path, which can create a shock hazard or fire hazard. Ground fault detection systems are designed to quickly detect and interrupt ground faults, which helps to protect people and equipment from these hazards. There are several different types of ground fault detection systems, including ground fault circuit interrupters (GFCIs), ground fault protection of equipment (GFP), and zero-sequence ground fault detection systems. GFCIs are designed to protect people from electrical shock. They are typically installed in areas where there is a high risk of contact with water, such as bathrooms, kitchens, and outdoor receptacles. GFCIs work by monitoring the current flowing through the hot and neutral conductors. If there is a difference in current between the two conductors, it means that some current is leaking to ground. When a GFCI detects a ground fault, it quickly trips and interrupts the circuit, which prevents electrical shock. GFP is designed to protect equipment from damage caused by ground faults. It is typically installed on large electrical equipment, such as motors, transformers, and switchgear. GFP works by monitoring the current flowing through the equipment grounding conductor. If there is excessive current flowing through the equipment grounding conductor, it means that there is a ground fault. When GFB detects a ground fault, it trips and de-energizes the equipment, which prevents damage. Zero-sequence ground fault detection systems are designed to detect ground faults in three-phase electrical systems. They work by monitoring the sum of the currents in the three-phase conductors. In a balanced three-phase system, the sum of the currents is zero. However, when a ground fault occurs, the sum of the currents is no longer zero. Zero-sequence ground fault detection systems detect this imbalance and trip the circuit, which prevents damage. Zero-sequence ground fault detection systems are often used in industrial and commercial applications where there is a need for sensitive ground fault protection. They can detect very small ground faults, which may not be detected by other types of ground fault detection systems. When selecting a ground fault detection system, it's important to consider the specific application and the level of protection required. GFCIs are generally used to protect people, while GFB is generally used to protect equipment. Zero-sequence ground fault detection systems are used in applications where sensitive ground fault protection is required. In summary, ground fault detection systems are an important safety feature that can help to protect people and equipment from electrical shock and fire. There are several different types of ground fault detection systems, and the best type for a particular application depends on the specific requirements. A grounded transformer is a type of transformer in which the neutral point of the secondary winding is intentionally connected to ground. This grounding provides a reference point for the voltage in the system and helps to stabilize the voltage during fault conditions. Grounded transformers are commonly used in power distribution systems to provide a safe and reliable source of power. There are several different ways to ground a transformer. One common method is to connect the neutral point of the secondary winding to a grounding electrode, such as a ground rod or a ground grid. The grounding electrode provides a low impedance path for fault current to flow back to the source, which helps to quickly trip over current protective devices and energize the circuit. Another method of grounding a transformer is to use a grounding transformer. A grounding transformer is a special type of transformer that is designed specifically for grounding purposes. It typically has a zigzag winding configuration, which provides a low impedance path for zero-sequence currents to flow. Zero-sequence currents are currents that flow only during ground fault conditions. Grounding transformers are often used in systems where the neutral point of the transformer is not readily accessible or where a high level of ground fault protection is required. Grounded transformers offer several advantages over ungrounded transformers. Firstly, they provide a stable voltage reference, which helps to prevent voltage fluctuations and transients. Secondly, they provide a low impedance path for fault current to flow back to the source, which helps to quickly trip over current protective devices and energize the circuit. Thirdly, they help to reduce the risk of electrical shock by limiting the voltage on exposed metal pots. Grounded transformers are required by the NEC in many applications. For example, the NEC requires that all services over 150 volts to ground be grounded. This requirement is intended to protect people from electrical shock and to prevent fire hazards. When selecting a transformer, it's important to consider the grounding requirements of the application. If a grounded transformer is required, it's important to select a transformer that is properly grounded and that meets all applicable NEC requirements. In summary, grounded transformers are an important part of power distribution systems. They provide a stable voltage reference, a low impedance path for fault current, and protection against electrical shock. Grounded transformers are required by the NEC in many applications, and it's important to select a transformer that meets all applicable requirements. A zero-sequence ground fault system is a type of electrical protection system used to detect ground faults in three-phase electrical systems. It works by monitoring the zero-sequence current, which is the sum of the three-phase currents. In a balanced three-phase system, the zero-sequence current is zero. However, when a ground fault occurs, the zero-sequence current becomes non-zero. The zero-sequence ground fault system detects this non-zero current and trips a circuit breaker or other disconnecting device to isolate the faulted circuit. Zero-sequence ground fault systems are used in a variety of applications, including industrial power systems, commercial buildings, and data centers. They are particularly useful in applications where sensitive ground fault protection is required, such as in systems with electronic equipment or where personnel are at risk of electric shock. There are several different types of zero-sequence ground fault systems. One type is the residual current system, which uses a current transformer to measure the zero-sequence current. The current transformer is installed around all three-phase conductors and the neutral conductor if present. The output of the current transformer is proportional to the zero-sequence current. Another type of zero-sequence ground fault system is the core balance system, which uses a special type of current transformer that has a single core with all three-phase conductors passing through it. The core balance current transformer is more sensitive than the residual current transformer and can detect smaller ground faults. Zero-sequence ground fault systems are typically used in conjunction with other protective devices, such as overcurrent relays and ground fault relays. Overcurrent relays protect against overloads and short circuits, while ground fault relays protect against ground faults. The zero-sequence ground fault system provides an additional layer of protection against ground faults that may not be detected by the other protective devices. When installing a zero-sequence ground fault system, it's important to follow the manufacturer's instructions and all applicable electrical codes. The system should be properly grounded and tested to ensure that it is functioning correctly. Regular maintenance and testing of a zero-sequence ground fault system is also important to ensure that it remains effective over time. In summary, a zero-sequence ground fault system is a valuable tool for protecting electrical systems and personnel from ground faults. It works by monitoring the zero-sequence current and tripping a circuit breaker or other disconnecting device when a ground fault is detected. Zero-sequence ground fault systems are used in a variety of applications and are particularly useful in applications where sensitive ground fault protection is required.